Section 3.1. In this section, we're going to look at determinants. If you recall in our last section, we've heard this term determinant before, and we used this to determine whether a matrix was invertible or not. We saw that when the determinant was equal to 0, that the matrix did not have an inverse. So how can we find out the determinant of any size matrix? So we'll see that a determinant is actually just a number that is assigned to a square array of numbers in a certain way. And as we continue on, we'll see different uses for this determinant. Let's consider this linear system as it is given. If we look at the coefficient matrix A, which is A11, A12, A21, A22, let's put this into REF. Getting the matrix A into REF, we notice that we must change row 1 to be A21 row 1, and then our row 2 will become A11 row 2, and we get this resulting matrix below. Now, applying this last row operation of R2 is now negative row 1 plus row 2, we get this resulting matrix, which is in RREF. Now, looking at this matrix, how can we guarantee that we have a unique solution? For us to have a unique solution for this system, then of course, we do not want this to equal 0. So what do we notice? That if A11, A22 minus A12, A21 equals 0, then we will not have a unique solution. So therefore, we do not want this to be 0. And if we look at this, we notice this happens to be what we said the determinant was. If we cross multiply A11 times A22 and subtract away A21 times A12 times A21, then we do not want this to be equal to 0. And in our last section, we noticed that this told us that if they were equal to 0, then we would not have a determinant. And so therefore, for this to be the case, we do not want this to be equal to 0. Now let's consider the 3 by 3 matrix. So if we look at this system of 3 equations and 3 unknowns, we get this coefficient matrix here. Okay. As we've done in the previous slide with the 2 by 2, if we are to put this coefficient matrix into RREF, then we have a system that looks like this. Notice here, let's take that back. This term here, this A11 times this delta, where delta is this equation here, for this to have a unique solution, we do not want this to equal 0. And so therefore, if this gives us the determinant of the matrix, that's a lot of terms. So do we need to memorize this? Let's see what happens. So again, looking at this coefficient matrix A, let's look at that delta that we discussed earlier. Okay. And what do we notice here? There's an A11 and an A11 here, so we can factor it out. There's an A12 and an A12 here, so we can factor it out. And there's an A13 and an A13 here, so we can factor it out. What do we notice about this value here? We have A22 times A33 minus A23 times A32. That happens to look like the determinant if this were a matrix here. If I were to take the determinant, which means I would multiply this term times this term, then it happens to be the determinant of this matrix. So what do we notice here? We have A11 times determinant of this matrix. So let's see where this has come from. What do we also notice? Let's call this matrix here that I have circled in red the matrix A7, sub I, j, where A sub ij is the matrix that results from eliminating the ith row and the ith column. So for this particular, where does our ij come from? We're going to get it from this first term A11. So what would that mean for us? If we take this A11, if we eliminate the first row and the first column, then I am left with this resulting matrix Aij. And so therefore, we can say that A11 times the determinant of A11 will give us this first term. Now, let's look at this second term. This second term here. We want to, again, look at this A12. So we're going to say that this is the determinant of A sub here 1, 2. So how do we get this matrix? We take the A12 and we eliminate the first row with the second column, because it is the 1 is the first row, the 2 is for the column. And what are we left with? We're resulting with this new matrix A12, A23, A31, and A33, which we notice is here. So we get this term here. Also notice that there is a negative in front of this second term. And if we look at this first term, it was the positive of this value. And now looking at this last term, it happens to be the positive of this value. So there's a pattern here. We have positive, negative, then positive. And likewise, if we take this A13 and eliminate the first row and the third column, we're left with this resulting matrix here, which we'll call A13. And so we have this last term. Now, using this formula here, we are going to now find the determinant of a matrix. We saw how to do a determinant of a 2 by 2 matrix easily. Now let's use what we saw in the previous slide to find the determinant of a 3 by 3 matrix. Before we go further, we want to look at some terminology. Some notations. So we saw that we use this notation here, DET, which is the determinant of the matrix A. We also might use this system here where we write A in 2 straight lines. This is not the absolute value. This stands for the determinant. Sometimes we might just write it as our actual, and I guess it's not equal, it's just equal. Let's do this here. We might say the determinant of and actually write our actual matrix that we have. And so we might see, in this form, the determinant of this matrix. So looking at this matrix to find a determinant, we want to find this here. Recall the matrix A, and recall this matrix that we said was going to be our determinant. So the determinant of A is equal to A11 times the determinant of that A11. So how do we get this? Let's see. So we have the determinant of A. We first look at this first term, and we eliminate this row and this column. And so we'll have 3 times the determinant of the resulting matrix, which is 3, -2, 0, -1. Then we have minus, and we look at our our second term, and it will be 0 times the determinant of its resulting matrix, which would be 2, 0, -2, -1, plus we look at the A13 term, which is 4, and get rid of its resultant, and we're left with this resulting matrix here. And now it is easy to find the determinant of a 2 by 2. We've seen this before. So we have 3 times negative 1 plus, minus negative 2 times 0, which I just get a negative 3, minus, what happens to this matrix? Do I need to actually find the determinant of this? If it's 0 times this, we know this whole term is going to go to 0. And then lastly, it will have 4 times the determinant of this matrix, which is 2 times 0, minus 3 times 0, which is 0. So we get a determinant of negative 9. So what other information does this tell us? Since this is not equal to 0, we know that the matrix A is invertible, which means it has an inverse. Now let's look at this 4 by 4 matrix. Using this same system, we'll actually see if we were to expand this, this determinant. This first term, this negative 1 to the 1 plus j, since this is the first row, that will give us this plus here. This tells us the sign of the coefficient. If I do the second one as 1 plus 3, plus 2, which will give me a negative. Likewise, a positive, then a negative. Looking at this equation here, what do we see? If we want to take the determinant again, we have our plus, minus, and since these terms here are 0, we can eliminate them. So we're just going to look at our first term, which is plus, and then we look at its resulting matrix, which is given here. And then we have a minus of a negative 1, and its resulting matrix, which is given here. Now we notice we still have the determinant of a 3 by 3. So we break this down further, doing what we've done before. So what do we have here? This will be a plus, a minus, and a plus. This will also be a plus, a minus, and a plus. And this came from the negative 1 to the 1 plus j that we saw in the previous slide. And so we will have this resulting matrix here. We have the 1 times, and for this term, again, we only have to look at this middle term because the others are 0. So that's our negative 1, and the resulting matrix was the 3, 2, negative 3, 0, given here. And then here, the negative and the negative give me a positive. And so I have to look at this term and this term. They're both positive. It is 1 times its resulting matrix when I get rid of this. And then this last 1 times its resulting matrix, which is given here. Now again, doing this determinant, now it's easy because we can do 2 by 2s. So what will we have here? We will have a negative 1 times 3 times 0 minus a negative 6. And so minus a negative 6 gives me a positive 6. Plus, my next term would be this 1 times here. This is 0 and this is 0. So 0 here. Plus 1 times, this gives me negative 9 minus 18. If we do the math here, we have a negative 33. So this is the determinant of the matrix, the 4 by 4 matrix A. Notice that it is not equal to 0, so therefore it also has an inverse.